Hello students, once again welcome back to my ML lecture tutorials here, and I'm back with lecture number 20 of machine learning, where I'm going to tell you what is classification in backpropagation algorithm. How can we do classification using backpropagation algorithm that we have seen earlier. So stay tuned with me and keep on learning. So before going into the things, we'll first of all check out what is backpropagation algorithm. However, we have already seen this algorithm in neural networks. While we were studying about artificial neural network, we have seen what exactly is the work of backpropagation, how does it work out. So as we have seen, this algorithm is probably, the most fundamental building block in a neural network. And it was introduced in 1916, and almost 30 years later in 1989, it was popularized by some of the researchers like Rumillard, Hinton, and Williams in a paper which was called Learning Representations by Backpropagation Arrays. So, when we talk about this algorithm, it is used to effectively train a neural network through a method which is called chain rule. Right. In simple terms, we can say that after each forward pass through a network, like from the nodes we are moving forward, back propagation actually performs a backward pass while adjusting the model's parameters like weights and biases. So we have seen the neural networks which consist of several neurons, and here we have in this network we have some input layer, we have some hidden layers, and then we have some output layer. So back propagation algorithms are, they are kind of learning algorithm which are, one of the most important developments in neural networks. And here, the back propagation that we talk about, it is basically the generalization of the Vitro-Hoff learning rule to multiple layer networks and non-linear differentiable transfer functions. Now, this learning algorithm is applied to multi-layer feed-forward networks consisting of processing elements with continuous differentiable activation functions. So the network associated with backpropagation algorithm are also called backpropagation networks. Now the aim of the neural network is to train the net out achieve a balance between the net's ability to respond and its ability to give reasonable responses to the input that is similar but not identical to the one that is used in training, which is called generalization. So here you can see the architecture. This is a multi-layer feed-forward network. Here, the first vertical set of nodes that you are seeing are the input layers. The next set that you are seeing of Z is the hidden layer, and the last vertical set of nodes that you are seeing, the Ys, are the output layer. So here you can see that it is a feed forward network where the inputs are feed and they are moving forward, they are passing forward from the hidden layer itself towards the output layer. So we have already seen that how neural networks can learn their weights and biases using the gradient descent algorithm. We have seen this. So there was, however, actually a gap in our explanation that we didn't discuss how to compute the gradient of the cost function. Now that's a quite gap. Now here See, we have already seen that how the neural networks where backpropagation works far faster than earlier approaches to learning, making it possible to use neural nets to solve problems which had previously been insoluble. So today, the backpropagation algorithm, basically is the workhorse of learning in neural networks. So this lecture is more mathematically involved than the rest of the learnings that we have done. Now, at the heart of backpropagation is an expression or the partial derivative of the cost function c with respect to any weight or let's say bias in the network. So the expression tells us how quickly the cost changes when we change the weights and the biases. And while the expression is somewhat complex, it also has a beauty to it, with each element having a natural intuitive interpretation. And so backpropagation is not just a fast algorithm for learning. It actually gives a detailed insight into how changing the weights and biases changes the overall behavior of the network. Now that's well worth studying in detail. Now here you can see the architecture of feed-forward network. So in feed-forward networks, often we have one or more hidden layers of sigmoid neurons followed by an output layer of linear neurons. You can see over here. These are the sigmoid neurons, and there could be more than one hidden layer. This is a hidden layer basically that you can see. So multiple layer of neurons with non-linear transfer functions basically allow the network to learn non-linear and linear relationships between input and output vectors. So the linear output layer lets the network produce values outside the range -1 to +1. On the other hand, if you want to constrain the outputs of a network such as between 0 and 1, then the output layer should use a sigmoid transfer function such as log sig. So here you can see the diagram. This one is the input layer, and this is the hidden layer that we have here. Now see the background picture. So here this slide describes teaching process of multi-layer neural network employing back propagation algorithm. So here you can see. So see this in ML or in machine learning, this back propagation, it is a widely used algorithm, basically for training feed-forward neural networks. And generalizations of back propagation actually exist for other artificial neural networks and for the functions generally, right? So these classes of algorithms are all referred to generally as back propagation. Now, in fitting a neural network, backpropagation computes the gradient of the loss function with respect to the weights of the network for a single input output example. And it does so, efficiently, unlike a naive direct computation of the gradient with respect to each weight individually. This efficiency makes it feasible to use gradient methods for training multi-layer networks, updating weights to minimize loss. Gradient descent or variants such as stochastic gradient descent are commonly used. So the backpropagation algorithm basically works by computing the gradient of the loss function with respect to each weight by the chain rule, computing the gradient one layer at a time, and iterating backward from the last layer to avoid redundant calculations of intermediate terms in the chain rule. So this is an example of dynamic programming. So we have seen the term backpropagation. It strictly refers only to the algorithm for computing the gradient and not how the gradient is used. However, the term is often used loosely to refer to the entire learning algorithm, including how the gradient is used, such as by stochastic gradient descent. Now, backpropagation generalizes the gradient computation in the delta rule, which is the single layer version of backpropagation, and is in turn generalized by automatic differentiation, where backpropagation is a special case of reverse accumulation or reverse field. So the term backpropagation and is in turn generalized by automatic differentiation, where backpropagation is a special case of reverse accumulation. The term backpropagation and its general use in neural networks was announced in, as I told you, in 1986. Then it elaborated and popularized in 1986, but the technique was independently rediscovered many times and had many predecessors dating to the 1960s. So a modern overview is given in the deep learning. So when we talk about backpropagation, it computes the gradient in weight space of a feed-forward neural network with respect to a loss function, where x denotes input vectors of features, y is the target output for classification. Output will be a vector of class probabilities like zero point 0.1, zero point 0.7, or zero point 0.2. And the target output is a specific class which is encoded by the one hot dummy variable, example 0, 1, 0. Similarly, there is a C which is called a loss function or a cost function. For classification, this is usually cross entropy (XC) or log loss, while for regression, it is usually squared error loss (SEL). Now, when we talk about L, it is the number of layers, and we have WL It is the weights between L minus 1 and L, where WLJK is the weight between the kth node in the layer L minus 1 and the jth node in the layer. Then we have F1, which is called activation functions at layer L. Now, for classification, the last layer is usually the logistic function for binary classification, and softmax for multi-class classification, while for the hidden layers, this was traditionally a sigmoid function on each node, but today is more varied with rectifier being common. So, in the derivation of backpropagation, other intermediate quantities are used. They are introduced as needed below, like bias terms are not treated specially, as they correspond to a weight with a fixed input of 1. Now, for the purpose of backpropagation, the specific loss function and activation functions do not matter, as long as they and their derivatives can be evaluated efficiently. You can see. So here you can see that each neuron is composed of two units. First unit adds products of weights, coefficients, and input signals. The second unit realizes non-linear function, which is called neuron transfer or activation function. Signal E is adder output signal, and Y is FE, which is output signal of non-linear element. And signal Y is also output signal of neuron. Now, to teach the neural network, we need training data set. The training data set consists of input signals like x1 and x2 assigned with corresponding target, that is desired output z. So the network training is an iterative process. In each iteration, weights, coefficients of nodes are modified using a new data from the training data set. And modification is calculated using algorithm which is described here. See, now, each teaching step starts with forcing both input signals from the training set. And after this stage, we can determine output signals values for each neuron in each network layer. You see? Now, the pictures below illustrate how signal is propagating through the network. Symbols like WXMN represents weight of connections between network input XM and neuron N in input layer. Now symbols yn represents output signals of neuron n, where y1 is equals to f1 wx1 x1 plus wx2 into x2. Here you can see all these things. In neuron, you can see the value is here. You see y1, the formula you can see. The same is with the second input that we have in the hidden layer. Let's see. This is the formula for the second. And again for y3, it is for the third output, it is f3 wx1 3x1 plus wx2 3 x2 3x2. Now this is propagation of symbols to the hidden layers. Symbol WNMN here represents rate of connections between output of neuron M and input of neuron N in the next layer. So here you can see all of the hidden layers, how you can propagate. Now, see, in the derivation of backpropagation, other intermediate quantities are used. They are introduced as, which are needed below. Like bias terms are not treated especially as they correspond to a weight with a fixed input of 1. And for the purpose of backpropagation, the specific loss function and activation functions do not matter as long as they and their derivatives can be evaluated efficiently. So the overall network is just a combination of function composition and matrix multiplication where Gx is equals to FL, WL, FL minus 1, WL minus 1 like this. And for a training set, there will be a set of input-output pairs like Xi, Yi. And for each input-output pair in the training set, the loss of the model on that pair is the cost of the difference between the predicted output Gxi and the target output Yi. So we have to note the distinction that during model evaluation, the weights are fixed, while the inputs vary and the target output may be unknown, and the network ends with the output layer. It does not include the loss function. During model training, the input output pair is fixed, while the weights vary and the network ends with the loss function. Now backpropagation computes the gradient for a fixed input output pair like xi yi, where the weights can vary. Each individual component of the gradient, they can be computed by the chain rule. However, doing this separately for each weight is inefficient. Backpropagation efficiently computes the gradient by avoiding duplicate calculations and not computing unnecessarily intermediate values by computing the gradient of each layer. Specifically, the gradient of the weighted input of each layer denoted by delta 1 from back to front. Now, informally, the key point is that since the only way a weight in WL affects the loss is through its effect on the next layer, and it does not linearly, it does so linearly. So delta 1 are the only data you need to compute the gradients of the weights at layer L. And then you can compute the previous layer delta L minus 1 and repeat it recursively. So this avoids inefficiency in two ways. Firstly, it avoids duplication because when computing the gradient at layer L, you do not need to recompute all the derivatives on the later layers like L plus 1, L plus 2 level each time. And secondly, it avoids unnecessary intermediate calculations because at each stage it directly computes the gradients of the weights with respect to the ultimate output, the loss, rather than unnecessarily computing the derivatives of the values of hidden layers with respect to changes in WALJ and WLJK. So backpropagation can be expressed for simple feed-forward networks in terms of matrix multiplication, or more generally in terms of the adjoint graph. I hope this is clear. Like in the next algorithm step, the output signal of the network Y is compared with the desired output value, the target, which is found in training data set. So the difference is called error signal D of output layer neuron. Now, the idea here is to propagate error signal T, which is computed in single teaching step back to all neurons. So the idea to propagate error signal D computed in single teaching step back to all the neurons, which output signals were input for discussed neurons. Now the weights coefficient WMN is used to propagate error that are equal to this used during computing output value. Only the direction of the data flow is changed. Signals are propagated from output to inputs one after the other. So this technique is used for all network layers. If propagated errors came from few neurons, they are added. So this illustration is given below. You can see here how the weights are calculated. So when the error signal for each neuron is computed, the weights coefficients of each neuron input node may be modified. In formulas below, you can see the differentiation Fe divided by Te represents derivative of neuron activation function, which weights are modified. So here you can see the formulas. These are the formulas given, where it is computed like the weights are computed like WL XL equals to WX1L plus N derivative of DFE divided by DEX1 and WLX2L, which is equals to WX21 plus N in this derivative 1 DFE divided by DENX. See how we have calculated it. So it is given for all the input and output that you are seeing. See here. Is again for W46 and W56. This is how we are calculating. Just see the diagram, concentrate on the diagram. So Now, as we have come to the end of this backpropagation classification, let's see what are the application of backpropagation. They have been successful on a wide array of real world data, including like handwritten character recognition we can do using this. Then we can have pathology and laboratory medicines using this, and we can even train a computer to pronounce English text like virtual speech recognition that we are using nowadays with the Google Assistant. So here's are some of the the examples, the applications of this backpropagation. The limitations of this is that gradient descent drug propagation is not guaranteed to find the global minimum of the error function, but only a local minimum. Also, it has trouble crossing the plateaus in the error function landscape. So this issue caused by the non-convexity of error function in neural networks was long thought to be a major drawback. But some of the researchers can argue that in many practical problems that is not. Then the backpropagation learning actually does not require normalization of input vectors. However, normalization could improve performance. Then we have backpropagation that requires the derivative of activation function to be known at network design time. So with this, I hope that you have covered up all the things and you are able to answer the questions correctly. So now let me take you to the MCQ part of this series. So these are the question sets. Question number one, two, and three. Try to answer them quickly. 5 and 6, there is a feedback in final stage of backpropagation algorithm. Yes or no? Next, the sixth question is what is true regarding backpropagation rule? And the sixth question says what is meant by generalized in statement backpropagation is a generalized data rule. So try to answer them quickly. We have seen all these concepts earlier in the lecture, so I don't think there will be a problem in answering these questions. Now let me take you to the next other question. 7, 8, and 9. What are general limitations of backpropagation? Is it the local minimum problem, slow convergence, scaling, or all the above mentioned? Is it, we have seen all these things, you can answer out of them. Question number 8 says, what are the general tasks that are performed with backpropagation algorithm? Is it pattern mapping, function approximation, prediction, or all of the above mentioned? So the ninth question says, does backpropagation learning is based on gradient descent along error surface? Is it yes, no, cannot say such kind of thing, or it depends on the gradient descent but not error surface? Now let me take you to the last question. 10th, how can learning process be stopped in backpropagation rule? So is it there is convergence involved? There is no heuristic criteria that exist, or on the basis of average gradient value, or none of the above mentioned. So this is the last question, and I hope we have already seen the explanation related to this question in today's lecture. So I hope you'll be able to answer this quickly and correctly. So just think upon it, 8, 9, 10th question, and try to answer it quickly. So with this, I hope you have learned a lot about backpropagation algorithm in neural networks. So here I'm stopping this presentation. In case of any doubt, you can just comment me back and I'll be happy to answer. So keep on learning and keep on watching with me as I'm coming over with some more important concept of machine learning in my coming lecture tutorial series. Thank you so much. Stay tuned.